Thank you for being pragmatic. I'd like then to introduce Chris Quigg, who has been a Simons Foundation Fellow with us for 3 weeks now. That's the 3rd week, yes. Who's giving us the first introductory talk on colliders with the evolution and a promise. Thank you.
Thank you very much. And congratulations and thanks to you and all the organizers for the intense time that we've had here. So I was asked to talk about what we learned from colliders, but all of you can do that. So I thought I would instead emphasize how we have learned to make colliders and a bit about what they've done for us and what they might do in the future. It turns out that there have been a very large number of colliders. One might have thought of these as exotic machines, as indeed they were 50, 60 years ago. But this is a list I've taken from the particle data group of the recent colliders. You'll see many of them are electron-positron colliders. Many of those of the recent ones, have been factories of one sort or another, Z factories with other things that they've searched for, and flavor factories, strange particles, charm particles, and B particles. A few of them are still operating today. So the first quiz question is to identify which ones are still operating today. My colleague Vladimir is going to give the answer in his talk, depending on the evolution between now and then. We've had a couple of hadron colliders. The first 2 of them were repurposed from the SPS, superproton synchrotron at CERN, made into a proton-antiproton machine in a single beam pipe, and the Tevatron collider at Fermilab, created in much the same way. I include the late lamented SSE because, as I remarked the other day, a former director general of CERN came to me one day very excited and said, "Chris, you should have built the SSE. It was really the perfect machine." This was not a surprise to me, but it's good to hear it acknowledged. Anyway, we didn't get that. We do have 2 operating machines at the moment, the relativistic heavy ion collider at Brookhaven, and of course the very flexible Large Hadron Collider at CERN. There has been 1 electron or positron proton collider, HERA, at DAISY. The particle data group also has a list of defunct machines, as they call them, and recent machines. And throughout my slides, there are explicit and hidden links. So if you mouse around the slides, you'll be able to get primary resources for many of these things. So where did the idea came from? The idea of colliders came from Rolf Widerøe in 1943. It's a name you may know because it was in perusing a paper by Widerøe that Ernest Lawrence conceived the idea of the cyclotron. Widerøe was accelerator engineer, very flexible guy. And there's a lesson here, not only in creativity, but in how you should spend your time. He describes being on vacation in Norway in 1943. His wife wasn't feeling well. He was feeling lazy. He went out and was lying on the lawn, and he looked up and saw clouds in the sky. It appeared to him that the clouds were colliding, probably at different elevations, of course, and that suggested to him that you could increase the available energy of particle collisions by having head-on collisions rather than fixed target collisions. And he also reasoned at that time that if you had particles with only one chance to collide, there was a very slim probability that they would interact with each other. And so it was better to have storage rings. And what you see up here is his first sketch of how those storage rings might be made. The particles are going in opposite directions and meeting at a certain place. He gives a charming description of this here. This is something that you can click on and read about. He was criticized immediately by his buddy, Bruno Tuschek, who said, you know, a kid in school could have this idea. What are you thinking? Isn't it embarrassing that you're going to get a patent on this? Nevertheless, he persisted and got his patent, which was issued in Germany in 1953 or so. Now, before we had accelerators, before we had colliders, physicists relied on found beams in order to make experiments. Found beams such as the ones found by the Curie in Paris in the decay of radioactive elements with the emission of alpha particles going at a fraction of the speed of light, and so very high energies. One of the crucial experiments done in this way using alpha particles from a radioactive source was the famous Geiger-Marsden experiment spurred on by Ernest Rutherford, in which they found a small number of particles bouncing back from a thin gold foil, which gave Rutherford the idea that there should be something small and dense and positively charged at the center of an atom, the notion of a nucleus. That inspired, I mean, there was an intervening war and other things, but that inspired many creative ideas for trying to get to the high energies that were thought to be necessary to make the collisions and to shake up the nucleus, find out what was inside it, and demonstrate that it really was there. The most adventurous that I know about was this one done in the late 1920s on Monte Generoso, near the Italian-Swiss border in the Ticino. This was done by three young Germans, Brasch, Fritz Lange, and Kurt Orban. They had the idea of building a gigantic antenna. They strung a wire and a mesh of cables over a distance of about 500 meters near the summit of Monte Generoso. And in their first summer in 1927, they were able to demonstrate by the length of the spark gap that would be jumped that they had isolated 18 million volts. So 18 million electron volts in the terminology we would use if these were put to use. They found that there's a gradient in the atmosphere all the time, but it becomes much more pronounced during thunderstorms. And so they had a great time during thunderstorms. They built a metal hut in which this man that you see up here, Kurt Orban, was in the counting house. And according to this article in the American journal Popular Science Monthly, he was the most electrocuted man in the world, or the person most struck by lightning in the world. Luckily, he was inside the hut, and so it was the hut that was struck rather than Orban. Anyway, this was full of promise after the first summer, and they returned in the next summer, having done work back in Berlin on how they would actually put this high voltage to use. Lamentably, during that summer, Orban fell from the antenna to his death, and his colleagues repaired to safer quarters of the laboratory in Berlin. Nevertheless, it's a wonderful illustration of the lengths to which scientists will go to do amazing things. It turned out that having millions of volts was not actually necessary in order to shake up the atom. This is at least one instance in which it paid to listen to a theorist. George Gamow, fresh from his PhD in St. Petersburg, had reasoned, he was thinking about alpha decay. And there was a puzzle because particles come out of radioactive elements with high energies, what seemed to be high energies at the time. But sending those same particles back didn't seem to do anything to the nuclei. So that led to the notion that you needed much higher energies in order to get inside and shake things up. Gamow reasoned that if you were an alpha particle inside a radioactive element, you didn't have much to do all day but run back and forth into the wall. And by quantum tunneling, you could eventually come out. And so his notion was that if you had a high enough current of not so high energy particles and shot them at the nucleus, some few of them would get in and you could disrupt the nucleus. So that's what Cockcroft and Wall, their famous voltage multiplier, and with it's of only between 125 and 500 kilovolts, were able to lithium-7 hit by a proton into 2 alpha particles. Lawrence, following this other idea of Rolf Wiederow, conceived the idea of the cyclotron, in which you would have an applied magnetic field, you would put in particles with low energy, you would give them a boost through a gap every time they circled around, they would go to larger and larger radii, and finally they would be excluded. Lawrence always thought big, and so he was determined that before doing any experiments, he should reach at least 1,000,000 volts to show that he was tough. Welcome. And so he was beaten in the race by the guys who listened to a theorist. Nevertheless, started a revolution with the cyclotron, which could be scaled up to larger and larger sizes. I should say that the machine of Cockcroft and Walton, their voltage multiplier, did not go away. For the first 30 years at Fermilab, for example, one of the early elements in our chain of accelerators was in fact a Cockcroft-Walton machine. It's fantastic because it's polished spheres. It looks like science. Everybody wanted to be photographed there. It was finally retired in favor of RFQs later on. As I said, Lawrence thought big, and having made this with Stanley Livingston, the first cyclotron that would fit in the palm of your hand, determined to build bigger and bigger ones. This is the magnet frame for the 60-inch cyclotron. His whole team inside. There's Lawrence. There's my friend Bob Wilson, who was the first director of Fermilab. That's Oppenheimer violating safety regulations as usual, and so on. And one of the things Lawrence was good at, other than getting big ideas and executing them with a good big team, was raising money. He found wealthy people, and he would bring them into the laboratory. And in this case, they let the deuteron beam out of the cyclotron and into the air. And you see a meter stick here. So he would bring you to the laboratory and say, well, you know, this person who's not nearly as enlightened or wealthy as you are gave me enough money to build this one. But with my brains and your money, think of what we could do. And this succeeded for generation upon generation of cyclotrons. There are still some very large cyclotrons in existence today, one at PSI, one at Triumph in Vancouver. They're about the same diameter, about 18 meters. Here's the one at Triumph, which is opened up for servicing. Even so, when it's collapsed to a height of about 46 centimeters, you can see that because the particles are spiraling out, it's necessary to exhaust a very large volume of vacuum. And that sort of put a practical limit on what you could do with cyclotrons. These machines today are characterized by low energies, but very high currents of protons that they can produce very quickly. And so in a certain range of energies, they are very important machines. For the early days of our subject, it was cosmic rays rather than artificially accelerated particles that gave the most information about what we now think of as particle physics. The early accelerators could contribute to nuclear physics, but for particle physics, they were not yet dominant. Cosmic rays have the property that they go to semi-infinite energy, however, the flux is very low. When the subject is new, a non-zero flux, even if it's low, is a good thing. The first discovery, I think, other than the discovery of cosmic ray itself, was made in Hess's observatory on the Haflickar in Innsbruck, just above Innsbruck, by two women from Vienna, Marietta Blau and Herta Wambacher. Blau was a genius at improving emulsions together with the emulsion manufacturers, photographic emulsion manufacturers, and they recorded the breakup of nuclei under the impact of cosmic rays, and therefore recorded three-dimensional images of the stars, the nuclear stars. So this is one of the early examples of recording a whole event. Today we talk about bubble chambers, electronic bubble chambers, emulsions. We're an early example of this. So you could really see the particles doing their business. In the 30s, 40s, and up to the 50s, cosmic rays were very rich in making discoveries that are the foundation of our subject. The positron, the muon, the pion, the strange particles were all discovered in cosmic rays. there was a famous, what's often called the last great cosmic ray conference in 1953 in Bagnères-de-Bigorre on the slopes, well, on a peak in the Pyrenees. It's also the Col de Tourmalet, where the Tour de France was a week ago. So it's way up there near Bagnères. The conference was there. Jim Cronin has written an account of it. He was too young to be there, but some of his teachers were there. And so he wrote an account. And it concluded with a talk from Le Prince-Raguet, who said, we have to keep running. We can't give up. We can't slow down because we're being chased. We're being chased by machines. And the machines in question were a new kind of accelerator called the synchrotrons. Synchrotrons were enabled by a joint discovery made by Vladimir Wechsler at the Lebedev Institute in Moscow and Edward Macmillan in Berkeley. And they came to the recognition that if you adjusted the magnetic field to keep pace with what would be the natural bending radius of particles getting higher energies, and tuned carefully the frequency of the accelerating voltage, you would be able, the particles would naturally attain a stable situation. It's called the principle of phase stability. And it means that they will sort of take care of themselves, and you don't have to evacuate the entire volume as you did in the case of a cyclotron. The first embodiment of this that led to big physics discoveries was the Brookhaven Cosmotron. Here it is. You see that it's a donut instead of a disk of magnetic place. So I was wondering, I had seen these pictures many times, and I was wondering what were these devices outside here. And I made up all sorts of stories that, you know, maybe it was a way of adjusting the size of the ring or the shape of the ring or something like that. It turns out that they're vacuum pumps all the way around, because although this is a much smaller vacuum evacuated space than a cyclotron, because the control over the beams was not wonderful, you still have a significant volume to evacuate. Next came the Bevatron at Berkeley. This is a machine that was constructed explicitly to make antiprotons. So it had an energy, beam energy for the protons that colliding with a fixed target was just enough to make antiprotons if they were there. It is hard for me to put myself in the mindset of the people who, having learned that there were positrons, thought that there was a mystery about whether antiprotons would exist, but we will be equally clueless to our successors. Anyway, this was done for that purpose. The antiproton and antineutron were found, and this was an evolution of the idea of proton synchrotrons. There are also a couple of electron synchrotrons built. Wechsler built one. There was one built at Cornell, and a few others around the world. In 1954, Enrico Fermi was retiring as president of the American Physical Society, and he gave a talk for the retiring president's address in which, foreseeing the future, but also mocking his colleagues a little bit, he said, well, you know, physicists are building these synchrotrons, now there are a few GeV, they'll want more and more and more. And he imagined that the ultimate limit would be to put magnets in Earth orbit, a low Earth orbit, and make an accelerator out there, free vacuum maybe. He projected the cost. He said it could come into operation 40 years later in 1994. It would cost $170 billion. You will notice that we have done much, much better than this. And it would reach an energy of about 3 TeV in the center of mass. So one may ask, why must accelerators be so large? One reason is simply the magnetic field necessary to confine them. Confine the particles. The radius, bending radius, is inversely proportional to the magnetic field strength. With iron magnets, You can get to 2 Teslas. With superconducting magnets, you can get to larger fields, but not infinite fields. And during the era of the plane synchrotrons, you also needed a large aperture to confine the unruly beam. So we showed Lawrence in his cyclotron magnet frame. Here's the Bevatron frame. You see it's also an enormous thing. This is around early 1950s that they built these things. Then came one of the great inventions in the history of science, which is the invention of what's called the principle of strong focusing, or alternate gradient focusing. This is a recognition by Christophilus working in Athens, by Courant, Livingston, and Snyder working at Brookhaven, that if you subject a beam not only to dipole fields to bend it around, but to quadrupole fields, which have if you have a single quadrupole lens, it will focus the beam in one direction, but defocus it in the other direction. And a miracle happens, which is you alternate focusing in one plane and focusing in the other plane. The net effect is to focus in both planes. And so this has now allowed much finer control over beams than we have ever had before. You can see here in this cartoon that putting these together acts just like a focusing lens in optics. And so this is a great invention. This is the key. All of our colliders, to many of our fixed target machines, to nearly every synchrotron light source in the world. Without this, it would be gone. Sadly, I mean, not that recognition matters to scientists, but if there ever was an invention that changed the world and should have had a Nobel Prize, this is it in my view. Maybe because there were 4 guys, maybe because there was a little question about who did what first. That never happened, but this really changed our world. And we need more such inventions. So how did it change our world? We've seen it in pictures that before strong focusing, magnet frames and beam pipes were gigantic. But here I've tabulated some of them. So Cosmotron, the Bevatron with those big magnets that we saw, the magnet size 20 feet in one dimension, 9 feet or so in the other direction. Immediately after, the alternating gradient synchrotron at Brookhaven, which is very similar to the slightly later proton synchrotron at CERN. You can see that the size of the magnets is cut down by a lot. The size of the beam pipes is also cut down. Fermilab main ring, the beam pipes were 2 by 4 inches, so 10 centimeters. The total, the Fermilab accelerator was 2 pi kilometers around. The volume under vacuum in that machine is smaller than the volume under vacuum in the Bevatron at Berkeley. So this was really enormous, an enormous improvement in making it possible to build machines that were under control. Fermilab Tevatron is even smaller, 70-meter beam pipe, and the CERN LHC is even a little bit smaller. Okay, so colliding beams themselves. Well, as Vitero noticed, if you want to have beams that collide, the beams have to be very dense, and you have to give them, in most cases, multiple opportunities to collide with each other. So in the late 50s and early 60s, around the world, there were a number of groups that started to take seriously this idea of making colliding beams. Once the strong focusing principle had been demonstrated, and you had at least the prospect of dense beams, you could contemplate this. So again, there are links here to the original papers. There was a study done by a bunch of people in the Midwest United States. There was work at Frascati, work in Novosibirsk. And the first one that I noticed back in my childhood was an experiment carried out at Stanford called the Colliding Beams Experiment, CBX, by, well, the person whose name is best known today as Bert Richter and collaborators. They made these 2 rings in very much like the sketch made by Vitero, in which electrons would have the opportunity to collide with electrons going in the other sense. And I heard about this when I was in college or something. There was an article in the New York Times, which is a big source of scientific knowledge at the time, saying that there had been a report at the Washington APS meeting by Bernie Gittleman, I think, in which he had reported that they were able to make these collisions of electrons. They recorded approximately one collision every 15 minutes. So contrast that with what we see at the Large Hadron Collider today. And so that was pretty impressive. The headline on the article was, "Atom Smasher Test Shows Way to Save on Energy." Well, I guess if the current president of the United States heard that, he would cancel it. Anyway, they noted that doing 300 MeV electrons on electrons was equivalent to an atomic electron being hit by a 350 GeV electron beam. We only arrived at 350 GeV electron beams at Fermilab many decades later in a tertiary beam made there. A couple of days later, I found from some other source that they were going to do this experiment and they didn't know what would happen. So I thought that was wonderful. You know, there was no answer in the back of the book. These guys must be brilliant. Fortunately for the enthusiasm of a young boy, they didn't say, "We are going to test quantum electrodynamics," which I would have found much less exciting. Anyway, there it was. And that accounts in part for my fascination with colliders. First E plus E minus. So Richter was adamant. Richter and Tushek had a colloquy in which Tushek said the only interesting thing is E plus E minus collisions. And Richter said, this is really hard. We're not going to do that until we can do electron-electron collisions. So they both prevailed in the end. So Tushek built the first machine called Ada in Frascati. It's a cute little thing, maybe this big around. In Frascati, although they could build a machine, they didn't really have a good enough injector to try to make the appropriate collisions. So they collaborated with the French lab in Orsay and moved it to there where there was a superior electron machine. And there they made the first electron-positron collisions. And the rest is history, of course. That's one of the mainstays of what we do. One of the early things they did with the evolution of Ada into what was called ACO at Orsay was to do positron into hadrons, studying the form factor, if you like, in dipions of the rho meson. This is not the original plot, but this is the most recent measurement of such a thing from Novosibirsk a year or two ago. And you see the very fine structure, including the indication of interference between the rho and the isospin violating decay of omega into 2 pi's, which leads to a constructive interference below the resonance, below the omega mass, and destructive above, and gives this characteristic shape from which you can learn things. The first Hadron Collider was built at CERN. This was a very adventurous thing to do at the time, late 60s, early 1970s, called the CERN intersecting storage rings. It was 2 independent rings that could accelerate and collide particles at, I think, 8 interaction points around the ring. It used to seem like a gigantic ring. Now you can run around it in 7 minutes. So it was a kilometer around. 2 independent rings using conventional dipoles at the time. They did PP collisions up to 62 GeV in the center of mass. They could alternate, they could change the energy independently in the 2 beams, and so you could move the center of mass of where the beam was happening in different ways and test things. So that was about 2 TeV fixed target, very big. Pretty good luminosity, millions of events per second, not just one, and they also stored deuterons, alpha particles, and for a little while, eddy protons. It was, in the words of its builder, one of its builders, Kjell Johnson, the finest instrument one can imagine for research in accelerator physics. So a great deal was learned from this. First of all, the confidence that you could do such a thing, which was not obvious to people. It had less success as a physics machine, and this was because of an error that is frequently made in our field, which is a failure of imagination for the wonders that will be there. And so the experiments were basically under-instrumented. We now say today it's obvious you should have a 4-pi detector at every place, that you're not doing some special things. People had single-arm spectrometers, and so there was plenty of stuff to measure, but many important discoveries, the JPSI and the Upsilon, for example, were there for the taking, but were not made. The one famous discovery was done by 2 experiments, special purpose experiments, a group from CERN in Rome and a group from Pisa and Stony Brook, in which they discovered that the total cross-section for proton-proton scattering was rising with energy. Before that, extrapolating up to 30 GeV beams or so, it was thought that it was approaching a common limit at high energy. So that was a great sensation for the time, and in fact prefigures some of what we know about and think about today. Sometimes the innovations that we need to build better accelerators come from other fields. We often say that Lawrence was the founder of the industrial strength laboratory. It turns out that even before Lawrence, Heikki Kämppläinen in Leiden had an industrial strength laboratory for low temperature physics. He was the first and for a long time the only person who could liquefy helium, so a little bit above 4.2 kelvins, and he used that to study the properties of materials, among which was a famous experiment in which he was measuring the resistivity of mercury. Mercury was chosen because you could distill it and make it very pure, and for some reason purity was supposed to be important. Turns out not to be. And there was this remarkable result that just below the boiling point of helium, the resistivity dropped to an unmeasurably small quantity. So that's the famous first miracle of superconductivity, the ability to carry electricity without resistive losses. If you go to his laboratory or to the museum nearby, you can see his motto, which was through measurement to knowledge. So he was all into making measurements, and this was one of them. It occurred to him immediately that if you could carry current without resistance, you could build magnets. And so he built a magnet. This magnet fits in just the palm of your hand. It's really tiny. It was made of lead wire. You can see it in the Museum Boerhaave in Leiden. And it reached the staggering field of 600 Gauss before pooping out. And it did this because lead turns out to be a soft superconductor that the superconductivity is annihilated by a rather small magnetic field. Nevertheless, the idea that you could do this was important, not yet for accelerators, because accelerators, it didn't exist yet, but just as possibly an instrument to do special measurements of materials, which was his real interest. This is fantastically busy, but a reward study. Most of our accelerator magnets until now are based on niobium titanium, which is here. One of the alloys found most definitively at Bell Labs in the 1950s. It's a wonderful material because it's ductile. It's not easy to make superconducting magnets, but on the scale of superconducting magnets, this is really easy to work with, the nice soft stuff. It takes us to higher fields than we would attain with ordinary copper magnets. So the LHC field is about 4 times the maximum strength that you could get out of iron magnets excited by copper. But nevertheless, it poops out of a certain field. This is shown for 4.2 kelvins. The LHC is operated at 1.8, 1.9 kelvins, so shown here. So it is a dream, the object of much work, to find substances that will allow us to go to much higher fields. And some of the magnets we'll hear about maybe in the next talk that we will be using in the HLLHC and in the successor machine, we hope, are niobium-3 tin. This is a substance which is less easy to deal with because it has to be reacted in place. It's not just a nice cable that you can make, but maybe we'll learn to do that. And of course, there's a promise so far, not completely fulfilled, of high temperature superconductors. They're in use now for current leads and such things, but not really yet in accelerator magnets that we can ramp. Anyway, this is a development we owe to other people, although we've supported it, but it's something from which we benefit and allows us to dream more about what might be in the future. So on the other side, we can ask, how can accelerators be so small? One of the reasons has to be the strong focusing and the fact that we can control beams. There are other elements to this. Large-scale cryogenic technology is essential. Active optics, either beam cooling or other things that we use to make the orbits under control and as small as possible. The evolution of vacuum technology, improvements in accelerating gradient through efficient superconducting cavities. So there is a step to the side that turned out to be very important. And that was to repurpose the SPS and the Fermilab original main ring into proton-eddy-proton collisions. This is an idea that percolated from Novosibirsk, was picked up by Carlo Rubbia and friends, and put into practice at the SPS. The originators are Gersh Butker and Sasha Skrinsky in Novosibirsk in the 1970s. The person who made the stochastic cooling work was Simone Vandermeer on the left, and Carlo Rubbia, person who was obviously a figure on a fashion magazine, was behind the physics. So I always loved this, which one of Carlo's young collaborators sent to me, because Carlo at the time was always seen wearing a suit, but he always looked as if he had slept in the suit because he spent most of his time flying back and forth between Geneva and Boston and Fermilab and who knows where else. So he was the dumpiest guy you ever saw in a suit. Nevertheless, he was tuned up for Woma Vogue, and there he is. You can show him that, and he'll remember me fondly, I'm sure. So this is an example of active optics where you take the characteristic of the beam at one point around the ring, you race across a diameter of the ring or a chord of the ring to arrive in time to correct the beam before it gets there. And that was the one of the great contributions of Vandermeer. On the left, you see what in the early 1980s was a very complicated high energy event. So you see all sorts of particles coming out, tens of particles, imagine that. And the great innovation of software was you could tell your computer only plot the ones that are straight lines. And then in this case, you see an electron and a positron going in opposite directions. Anybody can tell that must be a Z boson, as indeed it was. So this was a real discovery machine for the W and the Z. There were also some discoveries that weren't real, but it was a great innovation. So this is followed by the Tevatron. The Tevatron had the experience of, Tevatron Collider had the experience of the SPS collider to build on. And so my colleagues there made the best eddy proton source anybody will ever have. And we're able to use those eddy protons together with protons in the Tevatron, which is almost 1 TeV superconducting machine, and do experiments there which succeeded the experiments at the SPS collider. Here's an example of the beam pipes that you see in the apertures for the quadrupoles and the dipoles, and as promised, they're much smaller than the things that Lawrence and his entire team could fit inside of. Detectors seemed big in those days. This is all of 2.5 or 3 stories tall, the CDF detector. The great triumph there was to find the top quark at a mass of 173 GeV, lifetime of 0.4 yoctoseconds, and got a lot of ink, justifiably. And the world was ready to be shown that superconducting magnets for accelerators were possible. So when the first beam was circulated in 1983, even before we'd done any experiments, our colleagues, including me, jumped up and down and said, well, now we can be serious and build an interesting collider. First follow-up was to build the Hera collider, the electron-proton collider in Hamburg. That used refined versions of the Fermilab magnets, but basically the same magnetic field and the same general elements of the design. We had already had the notion from a little thought experiment in 1977 that if you could reach the 1 TeV scale, you'd learn about electroweak symmetry breaking. The thing that's fun about this is that we did this before the W and Z had been discovered. So we were sort of acting on faith that 1 TeV was a magic point for a magic tipping point, whether there would be, say, a Higgs boson or strongly interacting Ws and Zs and something like that. So that crystallized the notion that TeV scale was crucial and led to the notion that we could build much larger superconducting machines. So until this time, there had been the very productive flavor factories, like leading us to the discovery of JPSI, the extensive study of the epsilon resonances and so on. CERN at this time started constructing the Large Electron Positron Collider. So this is the 27-kilometer round ring in Geneva on the border. The CERN campus is here, triangle. Lake Geneva there, Jura here, the Alps over there. Itself, a very decisive machine, studying electron-positron collisions, making extensive measurements on the Z-pole that taught us about individual couplings of the Z boson to fermion pairs, and searching in vain, but correctly, for the Higgs boson up to about 114, 115 GeV. And that tunnel, as you know, has been reused for the Large Hadron Collider, again, a superconducting machine. The LHC is a machine in which there are 2-in-1 magnets. So things are arranged so that on one side of the magnet, the dipole field is pointing up, the other side down. So rather than having protons and antiprotons in opposite directions, you have 2 protons going in opposite directions, but being bent in the same way. At about twice the field as the Tevatron magnets. Many things have been done at the Large Hadron Collider. The great triumph, of course, is the discovery of the Higgs boson. Here is one event of a candidate for Higgs decay into real Z, virtual Z in the Atlas detector. People say, misinformed people say, you've only found one particle at the LHC. Well, my friends in LHCb have a different point of view because it turns out that 79 hadrons have been found at the LHC. Sometimes they're immodest enough to say that 75 of them have been found in LHCb. Nevertheless, it's quite a harvest, and many of them are of a character not foreseen explicitly, but allowed in the original quark model papers, which would have made a meson out of quark antiquark. So here we have 2 quarks, 2 antiquarks, probably pentaquarks, and so on. Lots of puzzles to think about in applied quantum chromodynamics. Well, the Higgs was an object of desire for a very long time. We now have it. We want to follow up. There are many detailed properties to be illuminated. We'll be doing some of that on 3 of the LHC and following runs of the high luminosity LHC. We have dreams of building an E plus E minus to Higgs plus Z Higgs factory. So we'll hear more about those. And there are many questions that we have, whether the Higgs boson and the Higgs field is the source of all the quark and charged lepton masses, what it has to do with neutrino masses, are there any partners for the Higgs, how does it interact with itself, which is important not only for the electroweak theory, but maybe for thinking about the the problem of the baryon asymmetry of the universe, back to the little thought experiment, does the Higgs boson that we found fully regulate WW scattering? And then there's something that's a little bit annoying, that if you do this most straightforward thing you can do, so totally mindless, and you say the Higgs has a vacuum expectation value throughout the universe, that contributes to the energy density of the universe at an amount that puts one Jupiter mass inside each of you. Now, I don't know that's excluded by any fundamental principles, but it seems weird. So there's something about the connection between vacuum energy that comes from quantum field theory and gravity that we haven't understood fully. I give you links here to a talk of mine in which I have 120 or so questions that we should be, to which I don't yet know the answers. And then there's 45, 50, something like that. You know, it's one of those things, it started out like a good idea before Snowmass. I was going to show the breadth of our field to our colleagues. And then it grows into a big talk. It really should be a course. It really should be a book. And if I were a better person, it would be at least a paper, but it isn't yet. And then this paper is fun. This was an exercise I did before the Higgs boson was found. My mother was always very supportive of me. And so I wanted to be able to explain to her why it was important that we'd found the Higgs boson, if indeed we did. And so I started considering what the world would have been like if there was no mechanism like the Higgs mechanism for spontaneous symmetry breaking, which turns out to be non-trivial to think through, but there's a little paper there that does that. Okay, let us not forget that progress is made by people not using colliders. So there are many cases in which people are making measurements at the and beyond. There's the recent work on G-2 of the muon, which needs theory to catch up, although it appears to be catching up. There's a first measurement from CMS of the magnetic moment of the tau lepton. If we could ever do that precisely, it's interesting because the larger mass of the tau means it is more sensitive to beyond the standard model contributions. On the other hand, the electron magnetic moment, if there's any justice in the world, should be only a test of pure quantum electrodynamics. There's stupendous measurements to, 11, 12, 13, depending on how you count, significant figures of the electric dipole moment of the neutron, of the electron. Those require, to make the theoretical prediction, precise values for the fine structure constant. There are two stupendously precise measurements of that, one from Paris, one from Berkeley, both amazing experimental feats. They disagree by 5 standard deviations. And the value measured for the electric dipole moment lies right in the middle of those two. So that's a place for more progress to be made. And one can only admire people who are able to do things like that, even if they're not the people we interact with every day. So what are the next steps? We'd like to have more interactions, higher energy, better control. There are basically 3 approaches. One is to improve the techniques we use to accelerate and manipulate the standard particles that we're familiar with, novel acceleration schemes, and then the possibility of accelerating novel particle species or combinations, including, for example, muons. So a few pictures of conceptions for doing this. One is the Future Circular Collider, EE or HH at CERN. Even bigger ring. This is the same size as the ring of the superconducting super collider, of which only 1/3 was completed. So it's a size that human beings have contemplated before. And we'll see what happens there. The idea of an electron-positron linear collider, this violates Vito's intuition that you should have things collide many times. But because electrons and positrons are fairly easy to make in large numbers, you can tolerate that inefficiency and hope to do wonderful things, maybe take advantage of polarization of at least one of the beams. And there's the idea, which has been the subject of the last 4 weeks, of muon collider. This has the promise that it's a relatively small way to reach very high energies. On the other hand, it's also a relatively complicated way to reach high energies. So we have to see in the end which um, which prevails or on what time scale we can make them prevail. Here's a sketch, I think this is due to Dave Neuffer, that shows that a collider ring could fit on the Fermilab site. I don't regard that as essential, but it's kind of cute if you already own the property, and we'll see where to go with that. So the last remark I'd make is that accelerators are central to what we do. Colliders have been very central to what we've done in the last several decades. We should remember that a tiny fraction of the accelerators in the universe, the man-made accelerators in the universe, are used for our subject. There are more than 30,000 of them worldwide. A few hundred are for research, synchrotron radiation sources and things like that, muon spin rotation and so on. They're also used extensively in industrial processes, medical imaging, isotopes, hadron therapy, food irradiation, cross-linking polymers. In fact, the last two were invented basically by one of the three boys on Monte Generoso, Arno Brasch, after he moved to Brooklyn. So we have an opportunity and a responsibility to give some things to society as well as to satisfy our own curiosity. I'd be happy to take questions and comments.
So, time for comments and questions.
Is it okay if I ask a historical question? So, yeah, you know, you in your famous work that where you pointed to the TeV scale as a scale for, you know, a natural scale for something interesting could happen. From a modern perspective, you could look at the Fermi theory and you would get the same scale. Just from the four fermion interaction, roughly the same scale. So my question is, so I was just told by Roberto Franceschini this morning, we were discussing this, that in fact Fermi didn't use that as the motivation for his TeV collider. He used some crazy motivation. So my question is, did anybody before, say, your work or before the days of the W and Z boson think about the problem in this way, that the Fermi theory breaks down at some high energy scale, and that might be an interesting scale to go to?
Yeah, so it's not quite the same argument, but obviously it was an inspiration for us. In the mid 60s, T.D. Lee and maybe C.S. Wu, the right citation is in my book, my textbook, noticed that, I mean, so you know that if you calculate the second order in the Fermi theory, it goes nuts, right? Diverges. And so a natural idea was it must be W boson, so something that would soften the interaction. And what they did was basically think about nu mu E to mu nu E, and you can calculate the partial wave amplitudes there, and you find that up to something like 600 GeV in the center of mass, you don't violate unitarity, but after that you do. So that shows that the notion of a W boson or something like it was inevitable. So I'm sure that must have been part of the motivation for people to look for W bosons, maybe not with a specific energy scale in mind. It was only later in the 70s that people noticed that by considering nu to W plus W minus, which is an easier thing than E plus E minus to W plus W minus, that there was a similar effect, that something had to come in to fix things. So I think that was known vaguely. You know, there was no actual theory at the time. In 77, there was, 77 is when we did that. The Weinberg theory was hardly taken seriously. Crucially, we'd had the discovery of neutral currents in 1973, not yet the discovery of W's and Z's. Still, you plow ahead and see what's happening. So we certainly had in mind the precedent of the four Fermi theory starting to violate unitarity and noticing that that had led to, at least conceptually, an important idea. But I have to say, when we started out doing that, the story of that is bizarre because I had done, we had, thanks to Ruby and others, and many people thinking of things at Fermilab, people were trying to think of ways to make W and Z bosons. And there were all sorts of claims all over the map. So I took a half a year or something and studied that extensively. There's a paper in Reviews of Modern Physics on that. And after I did that, and concluded that, you know, it wasn't that simple, but it wasn't that hard either, and tried to specify what the conditions would be. I must have been completely at loose ends because Ben Lee came to me and he said, you know, you look like you're at loose ends. Why don't you think about weak interactions at extremely high energies? It's like the chicken pox. Every theorist has to get it, and it's better to get it when you're young. So that was the beginning without knowing where I was going, where we were going. And we found this little result. There was, I have to say, at the same time, epsilon before, a very nice analysis by Teeny Beltman on the basis of one loop calculation using the experimental result that the rho parameter ratio of neutral current to charge current strength was around 1. And imposing that on the one loop corrections, Teeny could infer from data and theory that around 1 TeV was an important place. Now, ours doesn't have any experimental inputs, it's totally general, but it was in the air. That's why I like to say that it sort of crystallized what people were thinking about.
Thanks.
I wanted to clarify. I didn't say Fermi didn't know. I say he didn't write. It's not written anywhere, but who knows
So,
if he knew.
Fermi was dead for 10 years when Lee and Wu did this analysis.
Okay.
Maybe it was in his
Maybe
notebook
they got
before.
it from a drawer of Fermi. desk,
Exactly.
You know. So, but yeah, it still strikes me that some concepts that today are the way you teach these subjects essentially are not necessarily the way they were taught at the beginning.
Right.
And motivating the existence of anything by this kind of arguments today is natural. But these guys, they had all the instruments and the tools to do it. And I would be really curious to know how they were phrasing these things when a cutoff was ever used as an argument to motivate anything. If it can add anything, I think the calculation of Weisskopf for the lamp shift, I think, essentially introduces positrons.
Yeah.
So, but I'm not so sure how much conscious they were of what they were doing.
So there's a wonderful line from Steve Weinberg about the lamp shift. He was writing, Steve was a terribly gifted scholar, and he was writing a paper called Notes for a History of Quantum Field Theory. And he talks about the lamp shift, and he says the most important thing about the lamp shift is not that it changed the way we thought, but it taught us to take seriously the ideas we already had. And that is a trick, to know which things you think are just, you know, sort of interesting and which are central.
Hey, Chris, great talk. Thank you very much. Interesting history. I just wonder whether it's absolutely from the sky. A couple of weeks ago, there was a paper published and publicized in physics.org that people predict that black holes, rotating black holes, can be 100 TeV to 1 PeV colliders for particles rotating in one direction, colliding with particles rotating in another direction. What would be signatures and applications of such collisions? The luminosity of such colliders would be like of the scale of 10 to the 70, right? So do you think we might have any hope to basically use that phenomena for anything useful?
You know, the trouble with physicists is that they will never say there is zero probability of anything happening. So this came up originally, I think, in the context of Rick at Brookhaven. Someone said Rick is going to cause formation of black holes that will destroy the universe and all of that. So if it's true, you don't have to pay your insurance premiums because nobody's going to collect. I was at CERN the summer that came out, and so CERN people were very concerned about it. And I said, no problem, make me DG for the day and I will take care of this. And my solution was for proton-proton collisions, the persistence of the moon tells us that this is not going to happen because it's been bombarded by cosmic rays forever. Little less clear for the heavy ions. And so in the interest of an abundance of caution, we will not do heavy ions in the Large Hadron Collider. So that would, of course, lose the German delegation completely from CERN. And I thought it would put Brookhaven in a very deliciously uncomfortable position. So it wasn't serious. As you know, people tried to do the numbers, and you can show that the numbers, based on anything we know, the probability of calamity is vanishingly small, but vanishingly small is not zero. When people, especially people in the string community at that time were talking about the formation of mini black holes, what they never succeeded in doing convincingly was to make an argument or a calculation for what the formation time or formation rate of those things would have been. So if one can do better on that today, that would be interesting. If the phenomenon is there, even on a controlled level, it would be fun. But we can never promise that nothing will happen.
You also mentioned some possibility to use those black holes to accelerate stuff.
One PeV. So and luminosity again, probability of such collisions is probably zero, but luminosity, at least on paper, could be enormously high because very compact objects. Then we know that in the standard spectrum of the cosmic rays, yeah, you can get one PeV colliding 10 to the 21 particles with one proton in the atmosphere, for example. But you know how few of them we get, right? It's one per Earth per year, roughly speaking, right? If not less. If we have sources of one PeV particles close to some black hole, which generated at much higher rate, it would be interesting, at least opportunity to see, hey, maybe we can find something there. And this is hundreds of times, if not 1,000 times beyond LHC. So so question is, if it's real, can we detect something out of there? Can we see something?
This sounds like another one of those problems that you should take on when you're still young.
Okay. Well, we are kind of loose on times anyway, but
Okay.
let me see if I see other comments. We will have discussion anyway after the second talk. I forgot the schedule. I think now it's coffee.
Yep.
It is. Okay. So let's thank Chris once more. We go for coffee.